Fluid dynamics deals with motions of gases and liquids, and with how these motions are related to forces. For this film, we have designed experiments in which gravity, electromagnetic, centrifugal, Coriolis, in fact all body forces, as well as viscous forces, are relatively unimportant. The centrifugal and Coriolis forces referred to here are present only in rotating reference frames. The main force, accounting for the fluid acceleration, will be due to normal stresses, to pressures. All the experiments will be in steady flow. This is the test circuit used for many of the experiments. Water from the sump is pumped to the diffuser and into this large low-speed settling chamber. The honeycomb straightens the flow, and these screens reduce the turbulence level. The flow is accelerated by this nozzle into the test section and then discharges back to the sump. Our first experiments have to do with changes of pressure and velocity in the streamwise direction. Our first test section is a contraction of cross-sectional area. This is how it fits to the nozzle. Static pressure manometers are located at the upstream and downstream cross-sections. Now let's look at the experiment. Here is the diffuser, the settling chamber, the nozzle, and the test section. My colleague Charles Kahn is inserting the static pressure manometers. And now he has started the flow. We see that the pressure falls from the upstream section to the downstream section. What about the velocity of the flow? Since water is nearly incompressible, the volume flow entering the contraction must equal the volume flow leaving, or else mass would be created or destroyed. But the volume flow is equal to the average velocity times the cross-sectional area. So the area decrease should produce a velocity increase. The velocity field is shown here in half of a symmetrical contraction by tiny hydrogen bubbles electrolyzed at a wire in the water. Each fluid patch accelerates and shows the velocity increase with distance. Because of this velocity gradient, the front edge of each patch moves faster than the rear edge, and each patch stretches out. Water is nearly incompressible, and the flow is two-dimensional, so the area of each patch cannot change, and it becomes thinner as well as longer. The velocity increase in the contraction is coupled to the pressure decrease by Newton's law of motion. Let's see how. Here, the bubbles mark many streamlines. Let's imagine that this is a typical fluid particle. For thinking physically about the problem, it is helpful to use the streamlines S and the normal trajectories N as curvilinear coordinates. First, let's look at the forces and accelerations along S for the typical fluid particle moving with speed v along S. Here is the particle enlarged. Since there are no viscous stresses, the normal stress at a point is uniform in all directions. It is a scalar, which varies from point to point. The net force on the particle acting along S comes from the difference of pressure on these two faces to the pressure gradient, dP ds. The acceleration along S is related to the convective increase of velocity as the particle moves along S, and, in Eulerian description, is equal to v dv ds. From Newton's second law, force per unit volume equals mass per unit volume times acceleration, we get Euler's equation of steady motion along the streamline. This minus sign tells us that a velocity decrease in the streamwise direction is accompanied by a pressure increase, while conversely, a velocity increase is accompanied by a pressure decrease. This is a manifold. The pressure distribution is shown by the water levels in these manometer tubes. With the bleed valves closed, the average water velocity is the same at all cross sections, and there is a very slight pressure drop due to viscous forces. I'll reduce the volume flow at successive sections by bleeding water from the manifold. The pressure now rises. Since the area is constant, the velocity is proportional to the volume flow. Therefore, the velocity decreases. It is this streamwise deceleration which produces the streamwise rise in pressure. In an incompressible, steady, non-viscous flow, Euler's equation has a special integral called Bernoulli's integral. Along each streamline, the sum of the static pressure and the dynamic pressure is a constant. This sum is called the stagnation pressure. On any streamline where the velocity is high, the pressure is low, and vice versa. The highest possible pressure, the stagnation pressure, occurs where the velocity is zero. A very large reservoir supplying a flow to a duct system is itself a stagnation region. Here is a streaming flow past the blunt body with a central stream tube marked by hydrogen bubbles. The widening of this stream tube tells us that the flow is decelerating. The singular point where the central streamline reaches the nose is a stagnation point. The speed is zero there. On both sides of the unique stagnation streamline, the fluid decelerates, but not to zero speed, and then slides around the sides. The stagnation point is put to practical use in a pitot tube. The hole at the nose measures the stagnation pressure of the particular streamline reaching the hole. We've placed pitot tubes at the upstream and downstream cross-sections of the contraction, and these are the static pressure manometers we had before. The difference between the stagnation pressure and the static pressure is the local dynamic pressure. So this is a way of measuring velocity. Because of the area contraction, both the dynamic pressure and the static pressure change. But the sum of the two, the stagnation pressure, remains constant, which is what Bernoulli's integral told us. Bernoulli's integral also explains how we can produce suction by blowing. To show how a venturi can produce low pressure, we have formed half of a symmetrical venturi in this special test section that has one adjustable wall. A great many static pressure taps are in the straight wall and in the curved wall. Here it is set up for test. These are inclined manometer boards to show the pressure distributions on the two walls. We will observe the lengths of the water columns looking down from a position directly above. Now the flow is steady. We will look first at the pressure distribution on the straight wall. Continuity tells us that because of the area contraction, the velocity increases to the throat, and this causes a pressure drop. Downstream of the throat, the area increase produces a velocity decrease, and this causes the pressure to rise. At the upstream and downstream ends, where the cross-sectional areas are equal, the average velocities are also equal, and Bernoulli's integral would predict equal pressures. But the downstream pressure is actually somewhat less than the upstream pressure. This difference is due to viscous boundary layers, whose behavior we must always keep in mind, even when we pretend viscosity is absent. For instance, the area divergence here is much too rapid, and there is very little static pressure recovery in the diffuser. Far less than before. Even a very small amount of viscosity, if it leads to boundary layer separation, can produce very large changes from a truly non-viscous situation. In this experiment, water flows through a venturi that discharges to atmosphere. As we increase the flow, all pressure differences increase with the square of the velocity, and the pressure at the throat decreases. The gauge shows vacuum, and the pressure at the throat is now about 20 inches of mercury below atmospheric. Watch the throat. These patches that form are actually steam. This is cavitation. When the absolute pressure goes below the vapor pressure of about 1 inch of mercury, boiling occurs. The water changes to steam, and the subsequent collapse of the bubbles, which you can hear, creates enormous stresses in the wall. Mechanical stresses owing to the implosive collapse of cavitation bubbles on a surface do great damage to hydraulic machinery. And to marine propellers. Air from a hole in the middle of the upper disc is blowing against the disc below. To see how we could lift that plastic disc by blowing against it, we've instrumented this plate with pressure taps attached to manometer tubes below. 3 little spacers keep the disc and plate apart. This open tube shows atmospheric pressure. In these tubes, the water level rises when the pressure goes below atmospheric. At the axis, the pressure is greater than atmospheric by an amount equal to the dynamic pressure of the air jet. Over most of the plate, though, it is less than atmospheric, and rises to atmospheric pressure at the outer edge. The reason for this is that the through-flow cross-sectional area between the discs increases with radius. This area increase causes a fluid deceleration, and by Bernoulli's integral, a pressure rise. Actually, the viscous forces in the narrow gap are by no means negligible. But in this particular experiment, the mass acceleration forces are generally larger than the viscous forces, and so they govern the shape of the pressure distribution. The subatmospheric pressure over most of the area explains why the disk is lifted. Our flexible wall rig now is in the form of half of a rapid symmetrical contraction. We've discussed the relation between pressure and velocity changes along the streamline. But see how different the pressure distributions are for the two walls. To understand this, we must now think of the particle dynamics normal to the streamlines. This again is our system of streamline coordinates. At this point on the particle trajectory, the radius of streamline curvature is r. The net pressure force acting toward the center of curvature is due to the difference of pressure on these two faces, to the gradient dp dn. Although there is no velocity along n, there is an acceleration, v squared over r, toward the center of curvature. Setting force equal to mass times acceleration, we get Euler's equation of motion normal to the streamline. Here, the important thing is curvature of the streamline. The pressure always increases outward from the center of curvature. In this bend, the streamlines are curved. This is a set of 3 static pressure manometers in the straight section approaching the bend. This set is in the middle of the bend, and this set in the straight section following the bend. In the upstream straight section, the streamlines are virtually straight, and the 3 manometers show no pressure variation normal to the streamlines. This tall tube shows the stagnation pressure in the large upstream settling tank. The difference between this stagnation pressure and the static pressure at the upstream tubes gives a dynamic pressure of about 11 inches of water. At the middle of the bend, there is a pressure difference normal to the streamlines of about 3.5 inches of water. This is close to what we would predict using Euler's equation for the normal pressure gradient. Downstream of the bend, the pressure is almost uniform again. The slight variation there is due to a complicated secondary flow induced by the bend. As we increase the flow, all the pressure differences also increase, according to the square of the velocity. But the pressure difference due to curvature remains a constant fraction of the dynamic pressure. Another example of streamline curvature is the throat of this half venturi. The throat pressure at the curved wall is considerably less than at the straight wall because of the streamline curvature. When we use venturis for flow measurement, the pressure we measure at the wall is therefore not the average pressure at the throat. That is one reason for calibrating venturi meters. This bending of the jet toward my finger is the Coanda effect. A better experimental setup is this freely suspended hollow cylinder with a small static pressure hole connected to a manometer. Since the streamlines are curved, there must be a normal pressure gradient, with the pressure at the cylinder surface less than the atmospheric pressure at the outside boundary of the jet. The manometer shows that the pressure is less than atmospheric. Because of this subatmospheric pressure, there is a net force on the cylinder toward the jet. Now the manometer is balanced again. The Coanda effect is also part of the explanation for this. So far, we've looked separately at the pressure gradients along and normal to the streamline. To understand a complete flow pattern, however, we must consider both of these. And of course, we must also consider the equation of continuity to ensure that mass is conserved. Our flexible wall rig now is in the form of half of a rapid symmetrical contraction. Upstream, the pressures are equal on both walls. Downstream, they are also equal, but lower. Because of the area decrease, the average velocity increases, and, according to the streamwise equation of motion, the average pressure falls. On the straight wall, the pressure falls continuously, but on the curved wall, it first rises, then undershoots to a very low pressure before reaching its final value. Here are the pressure distributions superposed. Let's see how these pressure distributions may be predicted by the two dynamical equations and the equation of continuity. This curve of pressure versus distance shows the average streamwise pressure variation associated with the one-dimensional average velocity at each cross-section. Far upstream and far downstream, where the streamlines have no curvature, the pressure will be uniform over the two cross-sections. From the shape of the channel, we may expect that the streamlines will be of this general shape: concave up in this region, concave down in this region. These are two curves normal to the streamlines in the regions of different concavity. And these are the directions of increasing n, that is, outward from the center of streamline curvature. From a one-dimensional point of view and a comparison of cross-sectional areas, we may expect the average pressure on AB to be only slightly less than the upstream pressure. But because of streamline curvature, the pressure increases from A to B, so that the pressure at B will be greater than the pressure at A. Similarly, the average pressure on CD will be only slightly greater than the downstream pressure. Again, though, because of streamline curvature, the pressure will increase from C to D. So the pressure at D will be greater than the average, while the pressure at C will be less than the average. So the pressure on the curved wall rises to a maximum at B and then falls to a minimum at C. While on the straight wall, it falls continuously from A to D. According to Bernoulli's integral, which in this case has the same value for all streamlines, the velocity is a minimum where the pressure is highest, and it is a maximum where the pressure is least. The hydrogen bubbles verify this velocity distribution. The The tilting of these fluid lines shows that the velocity on the curved wall is at first less than on the straight wall. Here, near the beginning of the curve, the increase of stream tube area between the streamline and the curved wall shows that the velocity on the curved wall at first decreases. Near the end of the curve, the stream tube area reaches a minimum before once again increasing slightly. This minimum corresponds to the point of minimum pressure. Where the pressure rises on the curved wall, the viscous boundary layer thickens. If a rising pressure gradient is severe enough, the boundary layer might separate, or a laminar layer might become turbulent. To minimize adverse pressure gradients in wind tunnel nozzles, the contraction is made more gentle, as here. The streamline curvature is now much less, and the normal pressure gradients which caused the distinctive peaks in the pressure distribution are reduced. The flow is more nearly one-dimensional, and the pressure distributions on the two walls are more nearly alike. Bernoulli's integral is based on many restrictive assumptions. The statement that high velocity means low pressure is only sometimes true. Let's see how one could go astray. This straight duct has a partition. One side is free and clear. The other side has a flow resistance. Downstream of the partition, the two streams rejoin. The static pressures shown by these two manometers are equal. If you used Bernoulli's integral, you might conclude that the velocities of the two streams are also equal. Let's see. These are stagnation pressures, read by pitot tubes. From the two dynamic pressures, we see that the velocity downstream of the obstructed passage is less than for the clear passage. The reason Bernoulli's integral cannot be used here is that we are dealing with different streamlines. Because of the confinement of the channel walls, the streamlines are straight, with no curvature, and no normal pressure gradient. So the pressures on the two sides are the same, even though the velocities differ. For the same reason, the pressure across a viscous boundary layer is virtually constant. These vertical tubes will show the pressure distribution in the tank of water when we rotate it on the turntable. After viscosity brings the water into a solid body rotation, the velocity will increase linearly with radius. If you used Bernoulli's integral, which would be improper because you would be crossing streamlines, you would expect the pressure to decrease with radius. Actually, you see, the pressure increases with radius. This means that the stagnation pressure also increases with radius, and each circular streamline must have a different Bernoulli constant. The right way to look at this is with our familiar equation relating to streamline curvature. The outward radial pressure rise produces the net force which accompanies the centripetal acceleration. We have seen in this film a number of flows where the acceleration of each fluid particle was mainly produced by a single kind of force, the gradient of the pressure field. Finally, we must remember that we have left out many forces: gravity, electromagnetic, and so on. If these were present, the pressure field would have to balance them, as well as the inertial forces.